Now suppose we want to find the value of x that minimizes the cost, that minimizes f of x. So on the graph, we can already see that that point would be around here. But let's think about this problem a bit more deeply, right? So if x was equal to 2, if we were here on the graph, then the cost would be decreasing a lot as we're moving down. But when x is equal to 1, then that cost is still decreasing, but by not as much, because the line just isn't as steep, right? And by the same token, when x is equal to 0, that line is like flattening out even more. So at this point, the cost is only decreasing very, very slightly. Then we reach our minimum, and then the cost starts increasing again, right, as we move up the curve. So in other words, the slope or the steepness of this function, is telling us when we've reached our minimum cost, because that slope is the rate of change. And when this slope stops changing, well, on this graph, we know that the cost is equal to the lowest value. In other words, the slope of this function is going to be equal to 0 at the point where the cost is the lowest. Now, you may or may not remember from school how to find the slope of a function. Depends how long it's been, right? But as a reminder, the slope of a function is given by that function's derivative. So let's add this section heading down on the next cell. I'm going to go to cell type, markdown, put 2 hashtags there, and then write slope and derivatives, because this is what this lesson is going to be about. Now, as a challenge, can you create a Python function for the derivative of f of x and call that function df of x? I'm going to scroll back up for a second here. So remember, f of x was equal to x squared plus x plus 1. I'll give you a few seconds to figure this out. All right, so here's the solution, If you were scratching your head at this point because your calculus is a little bit rusty, let me show you what the solution is and also how we arrived at it. So I'm going to define a function with the def keyword, then I'm going to call it df, and have one input, namely x, colon, new line, return 2 times x plus 1. And that's it. So how did I arrive at this? How did I know it was going to be 2x plus 1? So the answer is I used calculus. Now, calculus and derivatives are a pretty big topic, but there's a couple of mathematical tricks or shortcuts that we can use to calculate derivatives very, very quickly. And one of these tricks is called the power rule. And we'll be applying it in several of the upcoming examples. So here's a very quick reminder on how it works. If you have a function, x to the power of n, then the derivative of this function is n times x to the power of n minus 1. So that's a pretty simple rule, right? Easy to remember. But before we move on, let me give you a couple of quick examples. So say we have a cost function that is, x to the power of 5. And we want to calculate this cost function's derivative. If we apply the power rule, then we simply get 5 times x to the power of 5 minus 1, which is 5 times x to the power of 4. And that's all there is to it. That's the function of the derivative. And here's another very, very quick example. We can apply the power rule to this function as well, x cubed plus 5 times x squared plus 7. So I'm going to go through these terms one by one. X cubed is pretty easy, right? Because x cubed will simply be 3 times x to the power of 3 minus 1. And then for that second term, 5x squared, the 5 stays where it is, and we have 2 times x to the power of 2 minus 1. And then that 7, right? That 7 just disappears. That 7 just drops. Because 7 is a constant. It doesn't depend on x. Constants don't change, and since the derivative is all about the rate of change, the constant drops out. It's equal to 0, so the 7 disappears. So what we end up with is 3 times x to the power of 2 plus 5 times 2 times x, right? 10x. And that's it, right? That's the power rule for derivatives in a nutshell. So back in Jupyter Notebook, say we want to graph our derivative function that we've just worked out here. We've worked hard to create it, so let's visualize it side by side with our original cost function. So what we want is we want two charts side by side. And to do that, we're going to have to use the so-called subplot functionality from Matplotlib. So I'm going to show you the subplot functionality, and I'm also going to show you how to size the two charts. So this is something new. This is something we haven't done before, but since a lot of the code will be very, very similar to what we've had up here, I'm just going to very, very quickly go to Edit, Copy Cell, and then go down here, and I'm going to go to Edit, Paste Cell Above. So I can reuse some of this code that we've got here. I'm going to change my comment here. I'm going to say plot function and derivative side by side. So this is what we're going to do here. And in order to size our plot, in order to size it, we're going to have to set the figure size of our plot. So we're going to write plt.figure, parentheses, and then we're going to say fig size is equal to, and then we have to give it a width and a height. So let's see what happens if I put in, I don't know, 10, 5 in the square brackets and hit Shift Enter. So you can see now that the width is 10 and the height is 5. I looked at the documentation for this, and this is actually measured in inches of all things. I don't really know why that is, but I hope it makes our American friends happy. Now I'm going to modify this code a little bit more. So in order to have two plots side by side, we're going to have to use this subplot functionality from Matplotlib. So I'm going to use plt subplot, and then I have to specify three numbers, a row, a column, and an index. So in this case, I'm going to have two plots side by side. So they're going to be in the same row. So one row, it's going to be two columns, and the first plot, this cost function here, is going to be at index 1. It's going to be my first plot. And now it's time to add our second plot. So I'm going to say plt.subplot, and for the second plot, it's going to be still in the same row, row number 1, still two columns, but this one is going to be at index 2. So this is going to be my second plot. Now I haven't added it yet. I'm going to do that now. To graph our derivative, we're going to write plt.plot. We're going to feed in our x_1 values, and then we're going to call our function, right? So the first one was f of x1, and this one is going to be df of x_1. Let's see what happens now if I press Shift Enter. Aha! So I've got two plots now. You see this? Two plots side by side, and they're still occupying the same space as before, right? The overall figure is still 10 by 5. So we can see here the figure size hasn't changed, but now it's split with two plots, two subplots taking up that same space. So I can probably make use of this space here on the right a little bit better by maybe making this 15 by 5. I think that should be about right. So I press Shift Enter, I get it like this. Very nice. Now what I'm going to do is add a few labels and style these graphs a little bit better so that if you're ever coming back to this notebook in the future, you can make sense of these charts very quickly and very easily. So I'm going to insert two comments first, right? So this is the first chart, and this is the cost function. And down here is the second chart of the derivative. For the first chart, let's explicitly state that it should be blue and that it should have a line width of maybe 3. And for our second chart, we're going to give it the color sky blue and a line width of 5. How does that look? Very good. Now let's add some title and X labels and Y labels to that second chart as well. So I'm just going to copy this code here and add it here, but instead of having it say cost function, I'm going to say slope of the cost function, and on the X it's still X, but on the Y it's going to be df of X. And then I'm also going to set the axes. So again, I'm going to copy xlim and ylim and add this down here, but I'm going to have it go from maybe -2 to 3, and from on the Y from say 3 to 6. Oh, sorry, -3 to 6. Yeah. So Shift Enter, see what it looks like. So this is quite good. This is very, very nice and clear. But there's one small improvement that I'd really like to make. We're interested primarily in where this minimum is here. And one of the things that'd be quite nice to see on this chart is where our slope, our sky blue line here, actually intersects the axis here. So what we can do is we can style our chart to have a grid. This is fairly easy to do. So for our second chart, for our derivative, all we have to do is add plt dot grid and then 2 parentheses for the method name. No need to add any arguments here. Hit Shift Enter, and then you can see Matplotlib applies a grid automatically to this subplot. And now it's very, very nice to see that our intersection of the slope of the derivative is going to be probably somewhere at the midpoint between -1 and 0. So that's going to be around here somewhere. That seems about right. So as a quick summary, we've covered 3 new things for styling graphs and charts. One of them is this idea of sizing them. The second thing is this idea of having plots side by side, and that requires the subplot function, which needs to know how many rows, how many columns, and what the index is. And then also we've used the grid function for the first time to superimpose a grid onto the plot. Now, as a challenge, can you, instead of having these plots side by side, stack them from top to bottom? What would you have to change in the Python code in order to achieve this, in order to arrange the plots in a different way? I'll give you a few seconds to pause the video and try it out. Did you solve it? Did you manage to get it? Here's the solution. The key on arranging the charts is going to be where our subplots are, right? So if you want to have them top to bottom, then you'd have to have 2 rows and 1 column. And I'd have to change this for both subplots. So for the first chart and for the second chart, I'm going to have to go 2 and 1 instead of 1 and 2. If I press Shift Enter now, we can see our charts arrange themselves from top to bottom. But one of the reasons why they look terrible like this is because we've constrained our figure size to be still using the same dimensions, 15 by 5, right? So it's stretching out the charts across the whole space that it's allotted, and that's why they look like this. But if we changed our figure size with some new constraints, say 5 and 15, right, then pressing Shift Enter will give us the charts like this. So in this case, they're more tall than wide. Now, I quite like the original setup, so I'm going to change this back to 15 and 5, and I'm going to go with 1 row, 2 columns for my subplots, 1 row and 2 columns for both of them. So this is how I would prefer to look at these 2 charts. But yeah, if you figure this out, it's super handy for being able to arrange the charts in your Jupyter notebook. All right, so I hope you're ready for the next lesson. I'll see you there. Take care.